So hello everyone, welcome this week as well as next week, and hopefully one more iteration after. We invited students to present their work. This week we have two students presenting on the topic of quantum dynamics. Sophia will talk first, and then Matt. Next week the two talks will be going in the area of quantum adiabatic physics and quantum physics, and hopefully we'll have more. But this is where I also wanted to suggest to students here, and also to tell your friends who are not here, please volunteer. Yeah, don't wait for me to volunteer you. It's your opportunity. You're spending enjoying 5 years doing your PhD, and then someone at the same time, maybe the same department, just have no idea what you're working on, and maybe there could be some interest, job interest, or now or later. So it's really an opportunity to tell people about your work and also practice just their presentations. You'll be surprised how you do it once and then it's easier the second time. So you feel more comfortable continuing with that. So with that, please, yeah.
Okay, thanks, Yuri. Thank you very much for the introduction, and thanks everyone for coming. As said, I will be talking about a new quantum algorithm we developed, which provides an improved precision scaling for simulating coupled quantum classical dynamics. And so the first question is probably, well, okay, why quantum classical? Why are we interested in that? And well, for one, you can generate wonderful pictures using DALL-E, using the quantum classical prompt. But on a more serious note, what you can also oftentimes, if you want to describe, say, the dynamics of a system, then a fully classical description is not accurate enough. If you think about, say, chemical reactions of larger molecules, then a fully classical description will just not do the job. So you might say, well, what about a fully quantum description? Especially if we're talking about quantum computers, then it should be fine to, just consider everything fully quantumly and simulate these fully quantum systems. But the problem is that these fully quantum descriptions become prohibitive for very large systems, even potentially on quantum computers. And the reason is as follows. These complex systems often exhibit separations of scales. And what do I mean by that? So, for example, if we consider a molecule, right, then we have, it's composed of nuclei and electrons. The nuclei are very heavy, and the electrons are very light, which means that in general, the nuclei will move on a much, much smaller spatial scale than the electrons. In particular, this means that we would need a much, much finer grid to actually resolve the wave function of the nuclei if we treated the nuclei as quantum particles. And okay, so this then suggests that, okay, maybe, it might make sense to treat some of the parts of the system classically and other parts quantumly. And so let me describe the setting then. And as I said, we split our overall system into a classical part and a quantum part. And the general idea is to say, okay, I mean, first of all, I guess it's not super clear how you do the coupling of your classical degrees of freedom and your quantum degrees of freedom. But the setting that we will consider, and that's also a very commonly studied one, is the setting where you have classical particles which move in a potential generated by the quantum particles. So, for example, what you will have is a Hamiltonian of this form, right? So you have, and this is a classical Hamiltonian, so P and X commute. So you have the momentum term, the kinetic term of one particle, the momentum term of the second particle, right, of your two classical particles here. Then you have a potential term, a classical potential term, which just stems from the interaction between your, between your two classical particles. And then you also have an additional term. This is really where the coupling comes into play. A potential generated somehow by the quantum particles. And I will explain in more detail how exactly we get this BQ. Okay. But then, so the general idea then is to just say, okay, we're now interested in the motion of the classical particles as they evolve in this potential generated by the quantum particles. And so the main results that we have is as follows. And the paper just got published this week, so feel free to check it out online. So what we do is we develop a quantum algorithm for simulating such coupled quantum classical dynamics. And our quantum algorithm is based on the Liouvillean formalism of classical mechanics. And I'll explain how that formalism works in a second. And what we show is that the gate complexity, so the number of quantum gates you need to simulate such dynamics, scales as follows. So you have this big O tilde, which is really just saying, okay, you're hiding subdominant logarithmic factors. And so the scaling goes like 1 over epsilon. Epsilon is the desired precision that you want in your simulation to the little o1. So little o1 just says, okay, it's smaller than any constant. So essentially subpolar the scaling 1 over epsilon. Whereas previous work, what they showed is essentially a way to solve a very similar problem using order 1 over epsilon gates. And that's what we refer to as the superpolynomial improvement in the scaling, right? We get the 1 over epsilon to the lower 1 scaling, whereas previous methods needed the 1 over epsilon scale. And the nice thing is with our framework, we can do simulations at constant energy. So the usual setting, which is the NVE ensemble. But we can also consider simulations at constant temperature rather than constant energy, which is the NVT ensemble. And that's really also what lots of people are interested in, say, in drug design or chemical reactions. And a priori, it's not so clear how to do these simulations in a fully quantum description. And then also especially using the NVT ensemble, we can estimate thermodynamic properties of our system, such as the free energy. Okay. So the main application I will be talking about is really molecular dynamics in this sort of hybrid quantum classical regime. And the idea is we consider the Born-Oppenheim approximation, which just tells us that we can separate the motion of our nuclei and electrons. And then going one step further, we treat the nuclei being very heavy as classical particles, but we do retain the quantum description of our electrons. And so what we get out then is, this is the Hamiltonian for our classical, for the nuclei. So you have this sort of H classical, which has the following form. It's a little messy because you have a lot of particles, but the main idea is you just have classical kinetic energy terms here for each particle. And then the second term here, this is just the Coulomb-Coulomb interaction between two nuclei. And again, that's classical. But then again, remember that VQ from the beginning. So the VQ in our case is this EL, which is the ground state energy of the electrons for fixed nuclear positions. So it's the ground state energy of this, which is now a quantum Hamiltonian, right? So in this case, again, you have the kinetic energy of all the electrons, but note that these are now quantum operations, right? So this is now the partial derivative. Then you have just the Coulomb-Coulomb interaction between the electrons. And then the last term is just the Coulomb interaction between a classical nucleus and a quantum electron. So this is the system or the types of system we will be focusing on. Okay, so it might help to just briefly see how, say, classical algorithm works for molecular dynamics, because this is a pretty standard way of dealing with these complicated systems using classical computers. So the idea is, right, as usual, you start with, you discretize your space, real space. You start with some initial configuration, so each dot represents now a different nucleus, right? And then you update your positions by integrating Newton's equations of motion. So you essentially compute the forces on all the particles which are indexed by I here. And this can also be written right as a gradient of some potential. And again, this potential V is either an empirical potential, or if you want to have more accurate simulations, then you will derive it from the electronic structure. So it will be the ground state energy, which I showed on the previous slide. right? So you compute the forces on the particles and you update the positions, and then you rinse and repeat for however many time steps you need to do this. And then the previous work I briefly mentioned, what they said is, okay, we can sort of quantize only the subroutine. What we can do is we can just compute the forces on the quantum computer and then do the integration, the numerical integration still in a classical computer. Problem is the scaling with that method will always scale like 1 over epsilon for each step, essentially because you actually need to extract the values of the forces to feed it back into the classical computer. So the problem here is really the sort of interface of the quantum computer used to compute the forces and then feeding it back into the classical computer. So that will essentially always give you this 1 over epsilon. Again, epsilon is the precision. This 1 over epsilon scaling. Recently, we also put out a work which introducing a new technique called amplified amplitude estimation, which in certain cases may allow you to improve on that scaling a little bit. You might get a 1 over square root epsilon scaling, which would be a quadratic improvement. But this is would only work in fairly restricted cases, but could still be interesting. Okay. Then the next ingredient we need to understand our quantum algorithm is the Liouvillean formalism. So let me briefly walk you through it, because that's essentially how we put, right? The question is, how do we put classical dynamics on a quantum computer? It might not be so obvious. And the Liouvillean formalism provides a very natural way of encoding classical information on a quantum computer. So what we start with is the phase space density, right? So essentially the probability density of finding the nuclei in a certain position configuration with certain momenta p at time t. And it's, again, as I said, it's a probability distribution. So if you integrate over all coordinates, essentially over all your positions and all your momenta, it needs to essentially integrate up to 1. And now the key point is the equation of motion for this classical phase space density has the following form. So you can see that the time derivative of your phase space density rho is just minus IL rho, where L is a Hermitian operator called the Liouvillean. And it's essentially the Poisson bracket with the Hamiltonian, right? So you can see it's just the derivative of your Hamiltonian. Again, this is a classical Hamiltonian with respect to the particle momenta. And then you have a derivative operator with respect to the positions. And then you sort of swap it around and change the sign for the second term. And again, yeah, that's the Hamiltonian we were looking at in this hybrid system. And again, the overall H is the classical Hamiltonian, just that this EL is generated by quantum particles. And now the great thing is that, well, L being a Hermitian operator, you can see that the formal solution to this equation of motion here is just this exponential operator exponential e to the minus ILT, which is unitary. And well, that's great, because unitary time evolutions are something you can do very naturally on a quantum computer. So that already looks very promising. However, there's still one problem, right? I was talking about the phase space probability density, which is the classical probability density, which is not quite clear how to encode that directly on the quantum computer. And there's another thing called the Koopman von Neumann formulation of classical mechanics, which sort of builds on the Liouvillean formulation of classical mechanics. And that used to introduce a wave function, the psi kvn, which again depends on all the positions of your classical particles, all the momenta. And the amazing thing is that this wave function also satisfies the same equation of motion, this Liouville equation, right? So the time derivative of psi kvn is equal to minus IL, where L is again the Liouvillean operator. And now the thing is that the phase space density rho can just be recovered via the sort of usual quantum mechanical computation of probabilities. So if you just multiply psi star complex conjugate with psi, that's how you would also in quantum mechanics just compute probabilities, that will actually give you rho, the one we're actually interested in, the phase space density. And the reason this works so nice, right? If you think about quantum mechanics, it's not that you can somehow, if you look at the Schrödinger equation, it's not that you can sort of evolve the square root in some sense of the wave function, and this will satisfy the same equation of motion as the actual wave function. And the reason it works so nicely for the Liouvillean is that the Liouvillean, this L operator, contains only first order derivatives. So if you take the product, it will still satisfy the same equations of motion. Whereas with the quantum Hamiltonian, you have second order derivatives. So if you consider the product of two wave functions, you will get mixed derivatives and it will generally not work out. So the upshot is what we're actually evolving on the end, in the end on the quantum computer is this Coupon von Neumann wave function, and we apply the Liouvillean operator. And then once we measure at the end, we will get essentially a sample of rho.
So 5 minutes.
Okay, thanks. And so the question now is, okay, we have the discretization, right, that I also mentioned for the classical algorithm, and the encoding, and a more visual representation. Okay, I think the second one you can't see. But the main idea is if we just look at panel A, for 1D, right, so you have essentially one dimension which represents your positions. We have one particle. It has a certain momentum, and then you map it to phase space. And the point is phase space has essentially twice as many dimensions because you treat position and momentum as separate variables, classically speaking, right? So here you can see the different positions with different momenta. You will map it to different points on the phase space. I'm not sure you can actually see you can't see the grid. Technically, there's supposed to be a grid here. And then each of those grid points of the phase space will be encoded as computational basis states on your quantum computer. And then the amplitudes of those computational basis states correspond to essentially the square root of your probability density. Okay, so now let's briefly discuss the quantum algorithm, the main thing we're here for. So the goal is, again, to implement this discretized evolution operator for your phase space density, e to the minus ILT. And what we do is we essentially do a combination of existing Hamiltonian simulation techniques. And the idea is to split our Liouvillean operator into two parts, a classical part and an electronic part, and then simulate, the details are not super important. The idea is essentially that you have one part where only the classical interactions are simulated, and then you have the second part where you get essentially all those the quantum potential. And you separate the evolution of these two parts separately. And then once you do that, you just recombine the evolution under these two pieces using a Trotter product formula, right? So first order just says, okay, if you have an operator exponential that is the sum of a couple of terms, you can simulate the evolution under the terms separately, and then just sort of alternate between the two to get an approximation to the overall evolution operator. And then you have some error scaling that depends on the commutator and the number of time slices R that you're using. And then the last question, I guess, is how do we implement each of these individual pieces? And they're essentially simulated using qubitization, which is a fairly, these days, a fairly standard way of doing Hamiltonian simulation. And the point is that simulating the part where we have the quantum contribution, this L electronic, it's not quite, that's probably the most non-trivial part of the algorithm because you don't have an analytic expression for your electronic ground state energy, which would be needed to just use qubitization. But using phase kickback, we can essentially reduce it to another problem that can be solved fairly easily. And again, the upshot is that our algorithm provides this improved precision scaling, the super polynomial improvement in the scaling with respect to the epsilon. Okay, let's skip this. Again, we also said we're showing how to do simulations at constant temperature. I don't think I have time to actually go through that. Maybe just briefly, the problem with the constant temperature dynamics is that the dynamics are unitary. So it's not directly clear how to simulate that on a quantum computer. But again, we can just invoke the treasure of a larger Hilbert space, which will come to our rescue. And the idea is essentially to we want to put our particles in contact with our heat bath at a certain temperature T. And there are ways to extend your Hilbert space to essentially just look at a larger Hilbert space, do simulations in the larger Hilbert space, and then just trace out the bath degrees of freedom to obtain the correct constant temperature dynamics of the real system. Okay. And for the summary and outlook, as I said, we provide a superpolynomial improvement in the precision scaling for simulating these coupled quantum classical dynamics, as I used to say for molecular dynamic simulations. It's based on the Liouville formalism, which allows us to essentially reduce the problem to a Hamiltonian simulation problem. And again, the paper is online, so please feel free to check it out. And here just some ideas for future work. And yeah, I think I'm out of time. And I'm happy to take questions.